Logistics is one of the lifelines of our economy. With globalization shaping our future economy, the need to transfer goods efficiently across countries becomes more and more demanding. We plan to provide a fast, economical, and environmentally friendly solution for logistics of goods across any terrain. Ideally, our vehicle drives off-road in the outback from point A to point B. Truck drivers traveling long distances are most likely to experience tiredness and fatigue. Fatigue affects the driving ability and the driver's reaction to avoid a crash in an emergency. A study based on coroner and police reports found that 30% of rural crashes in Western Australia could be attributed to fatigue, while 20 to 25% of all fatal car accidents in Victoria are caused by fatigue. In March 2010, a truck collided with a station wagon that was idled in N7's breakdown lane, killing a man behind the wheel. 2 weeks later, another truck ran into a group of cyclists riding in the bike lane of the N4, killing a man and injuring 3 others.
Our aim to provide a fast, economical and environmentally friendly solution for land-based logistics is demonstrated in our driverless system. Capable of off-road transport, this autonomous vehicle serves to provide a nationwide logistic pipeline between cities and industrial facilities such as mines and ports.
To accommodate the needs of today's transport industry, our trailer bed is capable of carrying a variety of standard payloads: 40-foot containers, 20-foot containers, bulk goods and materials. By complying with International Organization of Standardization rules, our solution is easily integrated with existing logistical systems.
Fifth wheel coupling provides a versatile trailer connection platform, allowing the clients to select an existing trailer based on their need.
TAC4 independent suspension improves maneuverability, ride quality, and off-road mobility. With proven success on thousands of defense, firefighting, and tactical vehicles, TAC4 tackles the most treacherous terrains.
Driving through rugged environments requires superior off-road capabilities such as superb shock absorbance, mechanical rigidity, and robustness. We have met these requirements.
The vehicle is driven by 3 70 kilowatt AC motors, where each is powered by a PWM inverter. The peak power output is estimated to be around 420 kilowatts. The nominal output is 210 kilowatts.
Our vehicle utilizes hydrogen fuel cells to provide constant power of an extended duration. To store a sufficient amount of hydrogen, the gas is compressed to 700 bars. The robot is able to drive up 500 kilometers using 120 kg of hydrogen.
To ensure fast data transfer between system components, CAN bus is employed on the vehicle. The Vehicular Terminal Explorer 727 turns our vehicle into a mobile communication hub. This, in conjunction with the Z402 GPS system, ensures we can monitor the vehicle all times.
To effectively scan the environment, 6 mid-range LMS 221 and 1 long-range LDLRS 3100 SIG lasers are utilized. The long-range sensor is used to detect the static conditions of the environment, whereas the mid-range sensors are employed to detect dynamic obstacles, thus ensuring the safety of the vehicle and bystanders.
Michelin's XZL all-terrain tubeless tires increases longevity, improves braking distances, and reduces rolling resistance, thus bringing fuel costs down. Providing excellent traction, these tires increase overall vehicle performance.
The chassis is pretty similar to that of a regular heavy-duty truck. It consists of a rigid steel frame of C-shaped rails riveted together by cross members running across them. The roll cage is a conventional aluminium Pratt truss used to house the hydrogen fuel tanks. These, in conjunction with a steel bull bar, provide superb robustness to the vehicle.
Once our vehicle reaches its destination, it proceeds towards a container warehouse where it undocks its load. Having achieved this, the head of our truck advances to recharging and maintenance facilities where it is always kept in good condition and its hydrogen supply is replenished. A control tower adjacent to these facilities coordinates the motion of all our vehicles within the compound. The tower initially gains control upon vehicles' arrival. All our vehicles are 100% independent. However, the The tower provides the overshadowing body needed for managing the vehicles collectively. The vehicle, now fully charged, can be dispatched to transport containers again, where it will progress to another compound similar to this one.
Based on estimations, the following costs have been determined. It is estimated that it would take 18 months to develop the vehicle, costing $1 million. Production time is estimated to be 3 months, costing $300,000. Following profits have been predicted within the next decade.
The occupancy grid is always updated by the vehicle sensors. For every new obstacle, a security distance has to be added around it in the occupancy grid. This is achieved by making the grid vary. The Dijkstra algorithm generates a cost matrix from the occupancy grid. Also a start point is needed, as it can be seen here. The output of the algorithm is a matrix that represents the travel costs from the start point to every reachable cell. All others are infinite cost. To get the path out of the cost matrix generated by the Dijkstra, a start point is needed. The endpoint is automatically the start point of the Dijkstra. The path is achieved by an algorithm that looks from the current cell at its neighbors. It goes there where the cost is the lowest. It determines when it reaches the endpoint. The path output isn't always optimized. Assume we have a field with a start and an endpoint. The Dijkstra output would mostly look like that. It can be clearly seen that the shortest way is the direct one. Optimizing the path is achieved by following steps. First, the points between edges are cleared. A travel function has to be created that we can still go from cell to cell. Furthermore, for every edge point, this function must check if it can skip the next edge point and go direct to the next one. If there is no obstacle in the new way, the skipped edge point is cleared.
To effectively simulate the logistical robot's operation, it is important to focus on its navigation, mapping, and its ability to reach a specified destination. The vehicle's main purpose is to transport cargo for a client from point A to point B, using the quickest path available. The first stage in developing the simulation was to build a program in MATLAB for sculpting the landscape in which the vehicle would be tested. This land sculpting program allows the user to manipulate the height of the land surface using a variety of tools, including a rounded brush for bulging or sinking a circular section, a rectangular brush for creating flat platforms, a ramp brush for constructing smooth transitions between heights, and a maze generator for converting image files into three-dimensional obstacles. The second stage was to define the vehicle's parameters and its interaction with the simulated environment. Vectors were utilized to represent the forward and upward directions of the vehicle. A rotation matrix was used to place the vehicle's skin appropriately. As the vehicle was moved over the landscape, the height of each wheel was independently calculated. From this, the height of the body was updated, along with the angle of the forward and upward direction vectors. In this way, the vehicle was able to hug the land over which it drove. The third stage was to recreate the manner in which the vehicle sensed its virtual environment. By reading in the points of the surrounding environment in a semicircular arc, the vehicle's SICK laser sensory was simulated. Differentiating this data, angles were calculated and the vehicle's occupancy grid was generated based on the vehicle's limitation. The fourth stage was calculating a path using a Dijkstra algorithm based on the vehicle's occupancy grid and driving the vehicle along this path until it reached its destination. The start and end points of the vehicle's path could be reset during the simulation. As the vehicle drove along, it built an occupancy grid using its virtual sensory and updated its path, bending it around obstacles. If the destination was unreachable, the simulation returned a string notifying the operator in the MATLAB console. After rigorously testing the vehicle through multiple environments of varying difficulty and layout, the vehicle was found to be largely successful in navigating, mapping, and most importantly, reaching its final destination. Oh my god, but hydrogen is like so dangerous.
No!
You see, hydrogen has actually been proven to be a safe, efficient and environmentally friendly energy source. Just ask my friend, Professor Oliver John.
Because electric and hydrogen power becomes the most important power source for cars in the future, the manufacturers and the government wanted to know about the risk before using this technology in everyday life. The University of Miami, in cooperation with car manufacturers, conducted an experiment which compares the severity of hydrogen and gasoline fuel leaks with ignition. So let's talk about this experimental setup.
This photo shows the hydrogen-powered vehicle on the left, gas-powered vehicle on the right. In the second photo, the ignition of both fuel cells occurs. Hydrogen flow rate is 60 cubic meters per minute. Gas flow rate is 0.7 liters per minute. Photo 3. The hydrogen flow is subsiding. View of gas vehicle begins to enlarge. After 1.5 minutes, the hydrogen flow almost finished. View of gasoline-powered vehicle has been expanded. 50 seconds later, the frame prior to interior deflagration. Deflagration in interior following frames shows flames existing around edges of trunk. Rear tire rupture. Driver side. Rear tire rupture. Debris out of passenger side of the vehicle.
The damage to the gasoline-powered vehicle was severe, while the hydrogen-powered vehicle was nearly undamaged. This proves that the usage of hydrogen is safer than common gasoline.
Our vehicle is fully autonomous. This will increase productivity since it can run 24/7 from start to stop. It also removes the possibility of human operation in hazardous areas and ensures better health of community by eliminating driver fatigue. Furthermore, it is environmentally friendly as it releases no emissions and reduces noise pollution through induction motor and fuel cell technology. Additionally, it is low maintenance and has off-road capabilities, which leads to faster deliveries.